Next up we have Matej, who's going to be talking about an introduction to Protokit. This is the Mina 01 Labs workshop. So please enjoy. Take it away.
Hi, my name is Matej. I'm one of the founding engineers of Protokit, which is a framework for building privacy-enabled application chains on top of Mina. You can see a bunch of our socials on the slides, so if you want to reach out, join our Discord, check out our website and let us know what you're building. This workshop is going to be quite developer heavy. There's going to be a lot of code snippets, so if you have any questions, please ask and I'll try to answer them ad hoc. And he has a mic as well, so yeah. Okay, so the first thing we need to understand before we get into explaining Mina and Protokit itself, we have to understand what ZK actually is and what proofs and circuits do. So let's go together from zero to ZK hero. So what is a ZK proof? So ZK proof is a mathematical proof of computation using either public or private inputs. It might include a public output too. The things that you can do in a zero-knowledge circuit might include things like signature verification, Merkle tree inclusion. We support different signature schemes as well, and a bunch of other cool stuff that you might want to compute as well. To actually compute a proof, you need to write a circuit, and that circuit is going to be written using a certain proof system. And the proof system that we use in the workshop is the same one as the Mina 01 uses, and it's called Kimchi. If you want to compute a ZK proof, you first need to run a circuit. So therefore, a proof is a result of circuit execution. And the circuit consists of constraints that determine the rules that need to be computed and valid for your proof to be valid as well. In our case, when we work with circuits, we have to compile them first. The result of compilation of circuits is verification and prover keys. The prover key helps you generate the proof, and the verifier key helps you independently verify the proof without knowing anything about the private inputs. Verifying the proof is also super cheap. That's why it's convenient to write circuits like we will see later. The zero-knowledgeness of the proof comes from the fact that we are not exposing the private inputs to the person who's going to be verifying the proof. That's very important to notice. So, we will be writing our circuits using O1.js, which is a ZK DSL built by O1 Labs. The DSL is written in TypeScript, so all of your circuits will be in TypeScript as well. Aside from simple circuits, you can also build ZK apps, which is the Mina equivalent of smart contracts. You can also use it to build ZK rollups, which is something that Protokit does, and many more cool use cases. O1.js itself includes a comprehensive library of common cryptographic primitives. There's functions for a bunch of different operations that you might want to do, like verify signatures, verify Merkle tree inclusions, and much more. It also supports infinite recursion as a property of the proof system itself. So any circuits you write are going to be infinitely composable with each other. Thanks to the fact that we are writing all of our logic as circuits, we can run them off-chain and submit the results of the execution to the chain itself. O1.js also allows you to write custom gates and gadgets to extend the building functionality of the framework itself. So there's also built-in custom gates and gadgets in the SDK itself for doing bitwise operations or field arithmetic, and a bunch of other features as well. So if you want to learn more about O1.js itself and about how to build on Mina, the first place you should visit is the official Mina docs. All right, let's skip directly into the code and let's take a look at how you can implement the circuit in O1.js. So the kind of a hello world example that I chose is a counter circuit, which allows us to keep a track of a counter, which is a UN64 number, and it can be incremented using the logic that's embedded in our circuit that we see on the slide. The way this circuit works is that it allows us to transition the counter state from one number to another, but it doesn't expose what the counter number actually is as a result or as an input. So the first thing we have to do when we're writing a circuit, we have to define the types that the circuit is working with. Namely, we begin with public input and public output. So in this case, both the public input and the output is a primitive that we called field. That's a basic building block of all the circuitry that we will be writing. I believe it's a 255-bit number. So our program, our circuit, will be taking a field as an input and also as an output. Our circuit is going to offer a single method called increment that additional to the public input and output is going to take further arguments, and these will be private inputs, and these will be of type UN64. So when we look below on line number 9 and we look at the method and how it's implemented right here, we notice the following. So the circuit code takes in a public input, which is going to be a hash of the counter state to keep it private because it's hashed, and then 2 more arguments. A is going to be the unhashed value of the counter, and B is going to be the number that we'll be incrementing the counter by. And the return value of that function is going to be a hash of the new counter state. So if we look through the implementation, so line 10 to 13, the first thing that we have to do is we have to verify that the private input that we have received, which is the unhashed state of the counter, or the pre-image to the hash, that is the public input, matches the public input itself. So in the circuit itself, we hash number A, we turn it into a set of fields, then we hash it, and then right below that, we assert that it matches the public input. So we give the circuit a hash, which is the hash of the current state, then we provide a private input with the raw state, and we make sure that we are providing a private input that matches the public input. Then we do the operation that we actually came here to do. So line number 12, we increment the 2 numbers. So the unhashed state plus the number that we want to increment it by. And as a result, right below that, what we do is we take the new state of the counter and we hash it again and we return it as public output. So I know this looks a little bit silly as an example, but it's the simplest that I could think of. What this allows us to do, it allows us to essentially hold like a counter state that is hashed, and if everybody in the room wanted to increment the number, and we would go person to person, the first person would choose the starting number of the counter, would increment it by a certain number, and then would have to tell the second person what the resulting number is, so they would be able to run the circuit again and increment the counter again themselves. So it opens up bunch of cool use cases like peer-to-peer MPC computation. So moving on, if you want to run the counter circuit, you first have to compile it. The result of the compilation is 2 artifacts. It's the prover and the verification key. The prover key obviously lets you generate the proof, and the verification key can be then used independently by the party that's verifying the proof to verify it. So in order to run the circuit, the first 3 lines of the code that we do here is we define the initial state that's going to be 0. Then we define the public input, which is going to be the hash of the initial state. And then we also define the number that we are incrementing by. Then we call the counter increment method itself. We provide all of these variables. And we wait until the prover generates a proof. So then we get the proof in as a return value. So what happens from here is that the public output of the proof itself is going to be the hash of the original state plus 1, since that was the number we were incrementing by. And we can also additionally, that's the most important step, we can verify that the proof of increment was done correctly using the increment, the counter increment circuit. So one more thing that's super important when we talk about circuits, and I've already mentioned it before, is that the circuits are infinitely recursive. What does that mean? It simply means that we can take 2 completely independent circuits. Proof of one circuit execution can be input to another circuit method, as we can see here as a private input. And that allows us to distribute the computation again, like between multiple parties. Like for example, you could do a proof of having some sort of ZK KYC, send it to me, and I could increment the counter on your behalf because the counter would only allow you as a KYC person to increment the counter. So that's a very, very powerful building block that we will be using later on. Now, let's talk a little bit more about why are circuits or proof systems important for blockchains. So we all know that blockchain is basically just a distributed database with consensus on top of it, right? Now, we know that users sign transactions and send them to nodes, which then execute the transactions, right? So if you are invoking a Solidity contract on an EVM chain, what happens is that you sign a transaction, you sign the parameters that you're providing to the Solidity method that you want to run, plus you specify the address of the contract that you want to execute. And then the node eventually executes that Solidity code on your behalf on the network itself. Once the node does that, when they produce a block, they just take all the user transactions, execute them, bundle them together, and we have a block. If you want to verify the block, or essentially bootstrap a node, you have to go through all the transactions since the start of the chain, re-execute them to ensure that you arrived at the same final block state as the rest of the network. That is what bootstrapping essentially is. If you want to do, if you want to design blockchains like this, like Ethereum did back in the day, you end up with a system which has quite high hardware requirements. Therefore, that makes it difficult for more and more participants to join the network and further decentralize the network. The thing that Mina does significantly differently is by turning all of that block production into circuits. Therefore, it can be proven. And when you bootstrap a new node that comes to the network, the node operator doesn't have to recompute anything. They just verify the proof of the consensus or the latest chain state. And thanks to this design, every block is essentially a single recursive proof that can be verified by anyone, including light clients, browser clients, or other participants in the network. So yeah, there we go. Apart from the chain itself, being cool because it's designed with ZK circuits from the ground up, Mina also offers smart contract capabilities. So let's take a look at how you can build smart contracts using O1.js on Mina. So you will have to install O1.js. That's pretty straightforward, npm install, and you can call it a day. The class that you will have to import to do that is called smart contract. That's pretty straightforward. We also call smart contracts ZK apps to, like, just so you know. Smart contract on Mina is significantly different, or like fundamentally different from a smart contract on EVM. As I've said before, if you want to deploy a contract on EVM, you have to take your Solidity code and send it to the node to be stored there to be executed at a later time. What happens on Mina is that you write a circuit, you compile it, and you only send the verification key to the chain itself. And then when you send transactions, you execute the contract locally on your device, let's say in your browser, and you only send the result, the proof of the contract execution, to the chain itself. So the chain itself no longer has to execute contracts anymore because you can provide a proof of the correct execution done by the client. This leads to some interesting benefits. For example, the chain being gasless, because you don't have to pay for any computation anymore because you do it yourself. So, I mean, you pay for it indirectly, but not with gas anymore. Yeah, leads to many different benefits. So, yeah, as I said, the contracts are executed off-chain. The transactions don't tell the node what code to run anymore. The transactions only send the proof of the correct contract execution, plus the changes that the contract is requesting to be made on the chain for the contract's account. We call these account updates. Yeah, so every transaction is a list of account updates. Each account update can be authorized either by a signature or a proof. And then when a block is being produced, a block producer or a node operator goes through the transactions that should be in the block, takes a look at every transaction, takes a look at every account update, verifies the proof or the signature that's attached to the account update and to the account itself, and applies the changes that the account update is requesting. The account update could ask the block producer to, for example, reduce the balance of the account, increase the balance of the account, change the state of the account, or any other things that might be a result of the contract's execution. All right, so we come back to the block proofs again. That's easy. One thing that comes out of the design of the smart contracts of Mina is that we have potential race conditions. And we have the race conditions because all of the contracts are being executed locally off-chain. And if you imagine two users trying to interact at the same time with the same contract, creating valid proofs of execution on top of the same data, and submitting them at the same time to the chain, then the first transaction invalidates the second one in most of the cases because they have computed the proof on top of the same data, but they transition from state A to state B, and then the second transaction tries to transition from state A to state C, so we have something that we call invalid preconditions. Okay. Let's take a look at how a counter smart contract would look like. So it's essentially the same circuit as we've seen at the start, but this time we have it as a smart contract. The only difference here is that with smart contracts, you don't really control the public input of the proof, but you have access to things like on-chain storage. The on-chain storage for every smart contract is limited to 8 fields worth of storage, where every field represents roughly 255 bits. So you have 8 times 255 bits of storage available. The API looks like the following. You just write a JavaScript class that extends the built-in smart contract class. You have to define your state properties on the class, plus you have to define your specially decorated methods that represent the contract code, which you can then run to issue account updates for the chain. So we again have an increment method that takes in 2 private inputs, A and B, like the previous circuit, but stores the commitment, aka the current state of the counter, as on-chain state. And again, the first thing we do, we hash the pre-image again to make sure that it matches the on-chain state. Then line number 8, we fetch the on-chain state. Plus we do this special piece of code that tells the chain that the proof that we are calculating, the proof of increment, is being done on top of the current on-chain state, which is the commitment to the current state of the counter. So if the current counter is 0, and you calculate the proof of the increment, it will create an account update, which has a validity precondition for the proof that the on-chain state counter's commitment still has to be 0 when the transaction is processed. So you can have a valid proof, but an invalid precondition because another transaction has changed the on-chain state before you. So that is what preconditions do. And then the rest of the code is equal to the first circuit that we saw, plus at the very bottom, we set the on-chain state again through the account update. If you have any questions, please feel free to ask. So if you want to run the contract, it's pretty simple. You just create a new instance of the class, use the transaction API, invoke the increment method as before, then you prove the transaction and you send it. Line number 8 shows you how the account update will look like after you run the increment method. So you're going to have an address of the contract that you're working with. You're going to have a set of preconditions that you have created during the execution, plus you will have instructions to update the on-chain state, plus it will have an authorization of type proof once you are done running the line 11. This diagram will hopefully clear up the whole account update thing and the client off-chain execution. So we start at the very bottom, where Alice is on her client executing the counter increment transaction, which produces a list of account updates that are part of the proof. That's the transaction that we will be sending. We will prove it, and we will send it. So we will send it to the network, to our favorite RPC provider, and the transaction will end up in a mempool. Now, what will happen? So we are on the chain itself, we are producing a block, and we have some initial state of the contract before the transaction has been processed. So we try to apply the transaction to the account. We use the account updates provided by the client. We authorize them by verifying the proof that is attached to the transaction and to the account update itself. If the proof is valid, or actually if it's not valid, then we revert and the transaction fails. If the proof is valid, then we also check the preconditions, and if they are not valid, we revert the entire transaction. If the preconditions and the proof are valid, we transition to the resulting state, which would be the updated counter commitment. All right, so I've previously mentioned that there's only 8 fields worth of on-chain storage for every account or every contract, which means that it's not really possible to do key value storage within the smart contracts natively. What you can do, however, is tap into a simple primitive called Merkle trees, which have this unique property that we will explain in the next slide. But essentially what it means is that every Merkle tree has a root hash, so there's a hash of all the data that is in the tree, and you can store that within your smart contract. And then within your circuit implementation, you can create a proof that certain piece of data is part of the tree so that you can work with it. So what's a Merkle tree? So Merkle tree is a data structure that allows us to cryptographically verify that a piece of data is part of a larger structure. We do it in the following way. So you see the entire tree as it is. At the very top, we can see the tree of, the root of the tree. We see a bunch of nodes that are there, and the leaves at the bottom or the nodes at the bottom are the actual data that we are storing in the tree. So this is a pretty small tree of height 2 or 3, I believe. So we can store 4 pieces of data here, which is not really interesting. But in reality, or in practice, we use trees that are much, much higher. So we can store, I don't know, billions of data entries there, and have the ability to like statically or quickly prove that that piece of data is still part of the tree. So if you want to write a contract that is using Merkle trees to store data, you would have to do a bunch of things yourself. The first thing you have to do is you have to figure out how to read data from a Merkle tree within your off-chain executed smart contract. So you literally have to prove that a piece of data is part of the tree, and you do that by fetching a witness and the data itself from like an off-chain storage service that you might have to implement yourself as well. And then within the circuit, you calculate the root hash by hashing your data with its siblings and the parent node with its siblings again until you arrive at the root hash, and then you can compare that to the data commitment that you are storing in the contract. So if you look at it line by line, so we are getting the commitment, that's going to be the root hash that we store on chain. Then we turn the key that we are using in our counter example to a field so that we can use it as a key for a Merkle tree. Then we get the witness and the actual value that we want to be using for our counter. Then we calculate the root using the value that we have received. And then if the calculated commitment to the root hash matches the stored commitment, then we can trust the data that we have received, and we can continue with the counter logic as we would have before. On the other hand, if you want to write data to the tree, it's essentially the same, but you wouldn't be using the data that has originally been in the tree, but you would calculate the root hash using the new data after incrementing it. Then you would arrive at a new root hash and store that in the contract again. So, what are the design limitations of this approach, right? So we know that contracts are executed on the client side, independently of other clients. We know that if we rely on on-chain state, that creates preconditions. And in our case, we would have a precondition pointing to the root hash of the tree. So that creates some interesting cases, which we will describe here. If we have 2 users transferring at the same time, their preconditions or the root hashes they have used to calculate the increment proof would be the same. And once one increment transaction goes through, it will change the root hash that's stored on chain, which will invalidate the second transaction. Here's a small diagram of how it roughly works. So again, we have Alice executed counter.increment using some arguments. She receives a witness and the data that she needs to work with the counter. That gives her account updates, which have a precondition to the root hash commitment. And if there's also Bob, who's doing the same transaction at the same time, they end up colliding on the precondition, which ends up invalidating Bob's transaction, which is not something that you want to do in practice because it would limit throughput of your apps. Okay, so our team has basically sat down and we tried to think about what can we do for ZK app developers that would solve these inherent issues or these properties of the smart contract system. And we arrived at the framework that allows you to build ZK rollups on Mina. Because if you think about it, even the original smart contracts are essentially like micro ZK rollups, because you have to run them off-chain anyways. So we thought, why not take it to the next level and provide an extra set of tools, an extra set of infrastructure that leverages recursive proofs to allow you to build essentially ZK app chains. So yeah, the name of the framework is Protokit. You can install it like using npm. It's very simple. It is also TypeScript based. It is based on O1.js, and it uses a bunch of quite a few recursive circuits under the hood to allow you to not have to do all the Merkle tree operations that you saw before. Focus on your business logic, ship your apps to your users, and let us worry about the infrastructure. So what is Protokit? It's a TypeScript-based framework for building ZK chains. It is not another ZK EVM-based framework. Instead, we use a ZK VM that we wrote ourselves. We support a hybrid execution model. So that means that, like with smart contracts, originally all the code runs off-chain on your client. With Protokit, what we do, we sequence the user transactions so that you don't have the precondition collisions or anything like that. But to be able to do that, we had to sacrifice the privacy property and take all the execution on-chain. That was the first step of the problem or the solution. The second step of the solution is introducing this hybrid execution model by allowing users to maintain the off-chain computation and send proofs to the sequencer that they have done something correctly. So that allows you to maintain your privacy, and we call that the hybrid execution model. So yeah, off-chain execution, client-side ZK proofs. The important thing to mention here, since every piece of code that you will write with Protokit is going to be a ZK circuit, plus also the underlying VM is also a series of circuits. It means that whoever is operating the ZK rollup, running the sequencer, has no room to lie about the execution, because all parts of the execution are proven and then eventually settled to Mina to be verified there. The entire framework is built from the ground up to be customizable and modular, so that means that we provide a bunch of stuff out of the box that you can reuse yourself if you want to, but if you feel like you don't like a certain part of the framework, you can throw it out, replace it with your own module, as long as it matches the interfaces that we ask for. So let's say that you don't like our mempool implementation, you can write your own and plug it into the framework. We were aiming for the learning curve to be as shallow, I hope that's the right word, as shallow as possible. So it should be relatively straightforward for you to pick it up during the weekend. Okay, so Protokit is meant to be used to build your own ZK rollup. As I've said before, ZK rollups are a series of recursive circuits. They can prove transaction execution and also rollup state transitions. State transitions are essentially instructions to our protocol that tell the protocol how should the Merkle tree state be changing. The L1 itself, so the Mina L1, offers sequence state and actions to help you build ZK rollups, but you still have to write your own circuits, like you've seen with the smart contracts. With Protokit, you can really easily build zero-knowledge, interoperable, and privacy-preserving apps, and you can build your own ZK rollups. Essentially, the ZK rollups that you build with Protokit are, in fact, the superset of ZK apps or the smart contracts, because we offer the same privacy features through off-chain execution and recursive proofs, but additionally, we also offer on-chain execution and sequencing, so you don't have the precondition issues that you might run into if you try to write your own off-chain state. So what is a Protokit ZK rollup made of? You have runtime, which is where your application logic lives. Then you have the protocol, which is where we take care of the block production, transaction fees, account state, nonces, state transitions, and everything else that you don't have to do anymore because we wrote it for you. Plus, you have the sequencer, where you have the mempool, the block production, settlement of the rollup state to the L1, and a bunch of other features. Of course, you also have the L1 settlement contract, which is a smart contract, as you've seen before, and the proof of the execution of your application change logic gets settled to the L1. Okay, So what kind of features do we offer? We offer a supercharged developer experience. So if you know TypeScript or JavaScript, it should be very easy for you to get started. All the modules are usable and open source, so you can just install them with NPM. You don't have any data race condition issues since we are sequencing all the transactions. The on-chain storage is not limited, like the one for smart contracts. You can essentially say that it's bottomless because of the Merkle tree size that we use. You can still preserve the off-chain privacy because we have the hybrid execution model, and you can just focus on shipping the business logic of your app. We are also integrated pretty well with all the ecosystem wallets that use the Mina signer standard. So yeah, one cheeky thing that I wanted to mention originally was that if you wanted to, you could re-implement even the smart contract protocol itself in your app chain with Protokit, but you probably shouldn't do that. Yeah. So some more things that we're working on. We're working on improving the interoperability between the ZK rollups. That's an important topic, and also data availability. So if you were to build a ZK rollup with Protokit today, you would be essentially running a Validium because there's no data availability guarantees built in today, but there will be. So yeah. So here we have a diagram that shows you how a transaction lifecycle might look like if you build your chain with Protokit. So we start on the client again, and we have Alice creating a transaction that calls balances.transfer, which is part of our runtime. She doesn't have to prove anything because there's no off-chain computer privacy necessary at this point, and she just has to sign the transaction and send it to the sequencer. If she wanted to have optional privacy, she could create a proof of a separate circuit execution built using the ZK programs we've seen before, generate the proof, and provide it as an argument to her signed transaction and send that to the sequencer. Now, when the sequencer produces a block, it will execute all the transactions that write from the users in a sequence. That means that first transaction has, I don't know, balance 1,000, then you do a transfer, okay, then the second transaction has a balance 500. So that's just sequencing or something that you would normally expect in an EVM environment. So once the runtime logic is executed, we end up producing what we call a set of state transitions, and those are instructions for the underlying protocol that tell the protocol how the Merkle tree state should be changing. And we prove even the Merkle tree operations, and then we merge the proofs together recursively until we have a block proof, which then goes back to Mina. Here's how you can write your own business logic. So it's very straightforward. Again, you extend a class that we provide out of the box, and you define some on-chain state. So it's essentially unlimited because the tree is so huge. Here we have a balanced storage between a public key and a UN64 that represents our balance. And we have a single method on the runtime that's callable by the users. So it's called transfer, and the arguments are from, to, and the amount. So the first thing you do is you fetch the state, then you do a bunch of assertions, making sure that the from address has a sufficient balance. You do an assertion here, then you subtract the balances, and you set them. So writing runtime code is really, really straightforward. Shouldn't be any different from, let's say, writing Solidity code, except it's TypeScript. You don't really need to be a ZK wizard or a mathematician to write circuits using OpenJS and how to also ship your app chains using Protokit. So if you want to write tests for a runtime that you have written, so you write the runtime, then you go write your tests, obviously. Or if you are feeling fancier, you write your test first and then you write the runtime. It's up to you. All you have to do is create an instance of a testing app chain within your unit testing framework. We use Jest. So you just specify the layout of your runtime. For this example, my runtime only consists of a single module called balances. Then you start the app chain, and you set a signer for your transaction API for the tests. Okay. Executing a transaction, a very similar experience to the Mina API. So first of all, you have to figure out which module you want to be calling. Then you forge a transaction. You provide the sender. Then you specify what transaction you want to be calling and what parameters you want to be using. You sign it. You send it to the sequencer. And then in test, of course, you have to manually produce a block, and then you can query the state of the chain through our query API, which under the hood is just the GraphQL call to the sequencer, and that gives you the actual balance that is the result of your transaction and then block production. Okay, so if you want to start hacking with Protokit, you won't find it in the Mina docs. You would only find smart contracts and OneJS itself. If you want to start hacking with Protokit, you have to go to protokit.dev and find our docs, which will lead you to the starter kit, which you can clone, install the dApps, and then just run a few commands, and you have a full chain running locally with an example UI, wallet integration, notifications, and everything else that you need for a hackathon to start working on your idea. This is what you would get if you install the starter kit. It's a simple example UI where you can connect the wallet and drip some tokens from a faucet, plus get notifications. What are we working on now? So one of the things that I'm personally super excited about is working on open treasury and governance for all the projects that use Protokit. We're also working on a privacy-enabled DEX called Copeng. And the things that I would like to see you guys work on are, for example, NFT standards, lending market, stablecoins, name services, credential solutions, ZK KYC, or whatever else you would like to work on. Yeah, thank you for listening. Please check out our website and let me know if you need help with building at our booth. Thank you. Any questions, maybe? No? You have a question? Yeah.
You mentioned that your Merkle tree is so big, it's basically like boundless. Mm-hmm. So like, how deep is it actually?
256. That's the height. I mean, it leads to some unwanted side effects, like the proving of the root hash calculations being relatively slow. But there are other designs that can solve that, like having index trees, which is something that we are currently in the process of adding into the framework. That's going to help us increase the throughput, for example.
Okay, thanks.
Thanks.
Relatedly, I'm curious, right now you say data availability is coming. How is the storage handled for all the state that you need to Merkleize presently, and are there any options?
So, can you repeat your question? Sorry.
So you're proving the off-chain state with this Merkle root, right? Mm-hmm. Who is in charge of storing that before data availability is available, as you were talking about?
Just the sequencer. I mean, by default, it has to be the sequencer, because to produce the blocks, to run the transactions, you need to have the data somewhere. So that's stored at the sequencer. The step after that is, of course, making the data available for the rest of the world, so that the sequencer is not the only one who can produce the blocks. That's like the basic premise of DA. Okay, thank you. See you at our booth.